Well, welcome everyone to our sixth Lake Stewardship Workshop as we continue our series on lake success stories. I'm Jim Irwin, Chair of the Rocky Mountain Biosphere Reserve. I'll be hosting tonight's workshop, and Dennis Hodgson and Daryl Kynes will be assisting. To begin, I would like to acknowledge that the Rocky Mountain Biosphere Reserve is in Treaty 2 and 4 territories of the Anishinaabe people, and say that we respect and share your all-important teachings that water is a sacred gift, essential for all life. Biosphere Reserve has been in existence since 1986, bringing people together to share their knowledge for the well-being of our communities. In this respect, we're pleased to have Jay Toews share the findings of his study of Kerr Lake in this session of our workshop. And Jay is a biologist and has a consulting company, go figure, Toews Environmental Consulting and Aquatic Sciences. Tonight, Jay will give us a presentation entitled Kerr Lake Nutrient Budget and Water Quality Study. Jay?
Yeah, thank you, Jim. And why don't I start there? I'd like to thank a few people that were involved in this. First of all, Jim and Daryl and Dennis at the Biosphere Reserve, thank you so much for putting on this workshop series and sharing knowledge. We have many lakes and they all have their challenges, and we can only do well to learn from each other. The study I'm going to present was actually funded and carried out by the Little Saskatchewan River Conservation District with my help. It couldn't have gone so smoothly or so well without excellent help from local residents and property owners around the lake. Lake Winnipeg Foundation provided some of the phosphorus analysis, and then the municipalities of Rosedale and Glen William Erickson also supported the study. So it's been a bit of a team effort, certainly, and it's been quite thorough. So let's jump into it. But before we do, with the title of the series, that these are lake success stories, I like that theme, and I'm going to carry that theme throughout my presentation in terms of what was successful and what we still need to be successful with. On that note, to me, a success story or a success has 3 steps to it. First of all, you need to learn what the problem is. And that's not always as clear as we might think, particularly with the complex dynamics of nutrients and algae in a recirculating prairie lake. Second of all, learn how to fix the problem specifically. And then 3, fix the problem. I'm not the kind of scientist who just likes to study things for the sake of studying things. I tend to be impatient. I want to see practical outcomes of what I do. That's why I left research decades ago and have been a consultant ever since. So I like step 3, but sometimes people are too eager, I find, to jump to step 3 and try to fix the problem before they really understand it. Even then, it's good to be it's not necessarily a bad thing, but it's good to be aware that there are 3 steps, and then we know when we're making a bit of a gamble or not, because we might be lucky and we might not be lucky if we don't understand the problem. So our case study with Kerr Lake, where are we? Well, with this study, we've done a great job of step 1. The Conservation District, they gathered great data, and we have a good understanding of what's happening at Kerr Lake. So that's where the success lies tonight. Learning how to fix the problem, well, we'll see. The Assiniboine West Watershed District asked me for a work plan that was submitted. We'll see where it goes, and then therefore we'll see if we get to step 3. Many people will certainly hope so. So let's, with that in mind, the 3 steps to success, let's jump into our case study. So Kerr Lake, Manitoba, for those of you that don't know, it's a little lake just about a mile long. It's right on the border of Riding Mountain National Park, down in what I've always thought of as the handle of the Riding Mountain Pistol. It's got 20 feet of depth at its deepest point. The shoreline is pretty intact with forest, and it's a very picturesque little lake. What else do we know about it? Well, it's got severe blue-green algae blooms. Quick note, Blue-green algae blooms, I prefer the more technical term of cyanobacteria. This is so widely used, though, that throughout tonight I'll just refer to them as blue-green algae blooms or algae blooms, and that'll be what I'm referring to. But back to the question, why does it, from what I just described, a 20-foot deep lake on the edge of a national park and forested country, why is it experiencing algae blooms? Well, let's have a closer look. Here's the lake itself. It's a headwater lake. What I mean by that, it has 5 very small inflowing streams. None of them drain more than a section or so. So it's a nice isolated lake. It doesn't have the issues that, you know, in an extreme case like Brian Martineau does with the Little Saskatchewan running through his lake. Surrounding it, there's a national park to the north. The section immediately east of it is it's forested crown land. There's it's mostly cattle pasture land around the other 3 sides of the lake. A few little details. Here's the cottage development. There are 16 or 17 cottages along here. There's another residence at the south end and a small campground at the south end, seasonal campground. Okay, so again, this doesn't seem like there should be too much of a problem here, and but there is a problem, and what's the problem? What is the solution? Well, let's see. Well, the problem is the lake is green, full of weeds, and it stinks. You know, an all too common problem on these prairie lakes. We've got the surface gums of the cyanobacteria. It might be hard to see on your picture, but far out into the lake are heavy growths of weeds. These are Myriophyllum and Ceratophyllum, these entangled messes that grow together. This is a common thing that we see. By the way, when the algae turns blue, it's just the stuff that's green in the lake, and then when it dies, it turns blue. And that's how it gets its characteristic name. Is this a problem or the symptom? Well, it's both. I mean, the algae blooms are a real problem, but just like the cracks in your walls or a leaky basement, it's actually a symptom of a bigger underlying problem. So what might that be? That's what I mean by step 1, and learn what the problem is in the success story. Okay, well, let's start on the study then. Now, anybody that knows me knows that I like to really look for local knowledge. You know, the people that actually live somewhere, they watch what happens year over year. It would be foolish for a scientist to go in with all the instruments and not collect some local knowledge. So in the Kerr Lake study, I started my local knowledge survey back in the early 1970s. And so this handsome young chap here proudly pulling his fish off the shoreline of the lake or off the dock there. While I was proudly pulling in my fish, my older cousins were out on the lake water skiing. I'm not sure how many people water ski on the lake today, but I can tell you that in that day, they did not come off the lake covered in green algae. What else did I notice at that time? Well, through childhood, I heard the grown-ups that were sitting on the cottage decks sipping out of stubby bottles. Well, they were grumbling about things. And I heard real concern about, at that time, in the early 70s, about how the lake water was starting to deteriorate. And they were really concerned about the cows on the far side of the lake as they were watching them, as they were sipping out of their stubby bottles. So that's where local knowledge starts, and has been ongoing since then. And so there was concern in the 70s of the water quality in Kerr Lake already. The local planning district board and the province of Manitoba, I guess, heard the concern. And in 1985, they did a study of the water quality and nutrient loading to Kerr Lake. And this, there was a report authored by Al Beck, and it identified a problem. The problem was excessive phosphorus loading to the lake. And that brought a recommendation to address that excessive phosphorus loading to the lake. And I'll actually read, it's almost prophetic here, but these were Al Beck's words back in 1987 when he wrote the report on the 1985 study. He said, Kerr Lake was subject to excessive rates of phosphorus loadings. Therefore, the water quality of Kerr Lake was expected to continue to slowly deteriorate unless ameliorative action was taken. Okay, well, what happened then? Well, some time went by and concern continued. I think the bottles changed, but the grumbling on the deck of the cottage stayed the same. And well, fast forward to today, and we've got the green stinky lake. Most of my pictures are from 2017, but this is the norm. I was there in 2015, and it was much worse than this, than my 2017 pictures. 2018 was a bad year. 2020 was a really bad year, apparently. So this is the norm there now, unfortunately. And this time the local conservation district heard the concern, and in 2018, they did a study of water quality and phosphorus loading in the lake. And that's a study we'll talk about tonight. And this is a spoiler alert to the results of the study. On the slide, I say things had gotten 10 times worse than they were in 3 decades earlier. By the numbers, phosphorus in the lake was 10 to 15 times higher than it was in the 1985 study, and the algae was 20 times higher. So I'd say this shows the importance of not stopping at step 1 on the 3 steps to success. Now, things may have been done in that time. I haven't been fully in tune, and I'm sure people have been putting in excellent effort, but it showed that something was missed and things became progressively worse on the lake over this time. Okay, well, then let's talk about the study itself with the scientific work. It included lake and stream sampling. The conservation district did the sampling itself. I helped them with planning and provided the training in how to do the sampling. And then I analyzed the data and wrote the report. This is just the front cover of the report. It's a big report. There's lots in it, and I'll just skim a couple of points tonight. It included a nutrient budget, comparisons to the previous study, and a limnological assessment to guide remedial actions. What that means is simply limnology is focusing on the interactions between the physical things, the chemical things, and the biological things in a lake. And that's what you really need to do to understand what's making the algae tick or bloom, as it were. In a nutshell, what this is step 1 completed to success. And it also gives us a little head start on step 2. So we'll talk about that at the end of the presentation. So, as I said, it included sampling on the lake at 3 locations. We sampled those, or the conservation district sampled those in winter and 3 times in the open water season. And it also included sampling in the 5 inflowing streams, 1, 2, 3, 4, and 5. And this sampling really focused on the early spring melt, which is when you get the big flush of water and the flush of nutrients. And then, thankfully, in a way, the year made it easy. It stopped raining, so the streams all dried up. So there was no water to sample in the streams after midsummer. And that was good, I think. It saved the conservation district some of the budget. So the stream sampling, what did that entail? Well, it was the chemistry sampling that we did, the water sampling focused on nutrients. Very important to realize that nutrients exist in different forms in the environment, different states of oxidation. They might be bound up in organic matter or free. They might be loosely bound to minerals, this sort of thing. So to understand how they're making the algae work or how they're making the algae bloom, you want to do the lab analysis to tease out the different forms of the nutrients, something like pieces of a puzzle. The other half, and just as important half of the stream sampling, was discharge measurements, because this is what allows you to calculate nutrient loads. So ultimately, we want to know what's happening in the lake. And with the lake, you want to know how much nutrient is in it and how much nutrient is coming in. And if I sample a stream and just tell you that it has a concentration of X, whatever it might be, the next question is, well, how much did you put in? Did you put in a gallon? Did you put in 10,000 gallons? So these 2 types of sampling have to go together when you're doing the stream sampling. And then there was a lake sampling. It focused on similar chemistry. that the stream sampling did, especially the nutrients and dissolved oxygen. But it also, we added some extra things which are important to really understanding what's happening. The metals, well, why are we sampling metals? The reason is that when you know the chemistry, understanding the metals dynamics gives you a more precise indication of what's happening with oxygen than simply measuring DO. And I'll give you an example of that later. A DO, by that I mean dissolved oxygen. Dissolved oxygen measurements are pretty crude compared to the metals analysis, because the metals change depending on how much oxygen is present. And they also are directly associated with internal phosphorus loading. That is the release of stored phosphorus off the bottom sediments. And so you need some of these corresponding variables to have confidence, especially when there's the prospect of spending money to try to fix a problem. You need to justify it by a few lines of evidence and by some more precise measurements than just the basics. So we measure all this chemistry, we measure stream discharge, we're measuring at the top and bottom of the lake, which is very important. What does it all mean, and how does this apply to algae dynamics or the algae blooms? Well, the answer is relationships among depths. Well, what do I mean by that? I thought it was about chemistry and water quality. Well, I'll show you. And to help illustrate, let's move off of Kerr Lake onto a very generic prairie pothole lake. That looks like a generic prairie pothole lake to me. I have to give kudos and commendation to my young son for providing some of the graphics tonight. I think it'll help us to visualize some of the things that I'm talking about. What do I mean by different depths and the relationships between them? Well, let's start. One depth is the depth of the lake, the total depth. So here we go. That's important to know. And yes, it changes around the lake, but it's important to understand that too. Another is the depth of sunlight penetration. Sometimes the sunlight can penetrate to the bottom, other times it can't. That's very important to know as well. How deep does the sunlight penetrate? Then there's the depth of mixing. How strong is the mixing, but how deep does it go? Does it drive oxygen to the bottom? Does it carry the algae around, or are they allowed to sink or float as they like to? Mixing is important. Mixing can come from different places. Wind mixing on the prairie lakes is dominant. Flow, if it's a bit of a riverine lake. If it's flow-driven mixing, then, and you have a control structure, if it's a regulated lake, then the configuration of the outlet is very important to how mixing works in the lake. By induced mixing, I mean things like aeration systems or pumps that actually drive mixing in the lake very intentionally to serve a purpose. So let's add some wind mixing to this. And this is the point here, is that it's the relationships among these various depths that lead to algae blooms through different mechanisms or prevent algae blooms. It's really important to understand this if you want to treat against an algae bloom, because you might have two lakes on the surface, they both look the same because they're both green and stinky, but they may have got there in a very different way in terms of how that algae bloom grew up and developed. And so if you don't know how you got there, then you might be kind of trying to cut off the wrong path of how it happened. So I mean, another way of saying that is if two lakes came by their algae blooms in very different ways, and you apply the same remedial action to the two lakes, should you expect that they'll respond the same way? Perhaps not. Now, with these different depths that are very important for interpretation, you can measure them directly. Sometimes that takes some expensive equipment and some finesse. And you can also get clues from other things that we're doing, like the chemistry that we do top and bottom. That's why we take measurements top and bottom. Algae community composition. Algae are not all the same. Some can float, some can control where they are in the water column, some sink helplessly. They have different nutrient and sunlight requirements. And so when you have different sunlight and mixing regimes that give rise to a different algae community, then you can think of it backwards too. If you have a certain algae community, it gives you a clue as to what the sunlight and the mixing regime is in the lake. So for the Kerr Lake study, we relied on chemistry and algae taxonomy. We didn't measure any of these mixing or the sunlight penetration depths directly. But I'm going to pause here for a moment. It's often good to make comparisons to other lakes. That's one way we learn. I'll mention another would-be or should-be lake success story in the region. The same year as this, I was leading actually a study on Shoal Lake. And in that one, we did measure more of these things, including light penetration. And part of the reason we chose to do that is that that project was all about depths, actually. The purpose of the project was to establish target operating levels so that the municipality could get a license for their dam. Otherwise, the dam was going to be removed altogether, and Shoal Lake would not be the Shoal Lake that we've come to know over the years, because the dam wouldn't be there, and it was to be returned to native prairie level. So with all the sampling we did and the extra measurements and the sunlight penetration, the results clearly showed that adding a couple of feet to the lake would not improve the lake water quality at all. As a matter of fact, it would be more likely to make blue-green algae blooms more severe and more frequent. So that, together with all the other work we did on the lake, helped us focus in on a series of target water levels or operating levels that were appropriate given all considerations, including water quality and shoreline erosion and this sort of thing. So that was a very thorough study as well. Step one to success in terms of next steps in remediating the lake, because there are some very severe algae blooms. Unfortunately, I'm hearing that many people say that they want the lake higher again. Unfortunately, it's a decades-old debate in the community. And why are they saying that, that they want the lake higher? Well, it's because they're being told that a deeper lake will mean better water quality or a healthier lake. And that's really unfortunate, because to say that ignores what we've already learned about the lake, and also ignores the legal realities of operating a control structure. So it's really preventing the community from moving forward, unfortunately. But I wanted to point it out because we do have another data set that draws great parallels in two very different lakes, Kerr Lake and Shoal Lake. So, but let's jump back to our case study of the evening, and that is Kerr Lake. Okay, the results of the studies. First of all, low dissolved oxygen in winter, 1.6 to 3.3 milligrams per liter. That is not enough to support sport fish, so that's troubling. High nutrient concentrations, and I'll pop up some basic numbers here. These are high. Interestingly, there's lots of phosphorus, lots of nitrogen, at least during the winter and fall, and I'll explain that a little bit. And an interesting point that I'd like to draw your attention to is that between March and September, that's the first time we sampled, and the last time, the nutrients increased quite markedly. That's a bit of a concern, and it speaks to internal loading, which we'll talk about in real terms soon. What else did we learn? Well, when you have that many nutrients, those high nutrient concentrations, of course, you get massive algae blooms, and they were pretty bad. The chlorophyll A was up around 300 micrograms per liter. For anybody that recognizes these numbers, these are all pretty high numbers. A real concern in the algae bloom was that there's more than 99.9% of phanosomenon, which is a floating, scum-forming, potentially toxin-producing, nitrogen-fixing, what other descriptors can I throw at it? But it's a blue-green algae, and it's our common one in these lakes. But when you see such a monoculture of algae, that's a real broken ecology in the lake. So certainly some concerns in the water quality. For people that like a lot of charts, have a look in my report, but I'm just going to give a couple. I promise only a couple in this presentation tonight. And this is how everything works together. So I'm not sure if you can read all the legends. It doesn't matter too much, I don't think. I'll point a couple of things out to you. This is through the year, our March sampling, June, August, and September. The bars, there are these columns, are the algae concentrations. This is a chlorophyll A concentration. No, they're not actually. They're the actual biovolume of the algae species. Here's your list of algae species that make them up. All you can see are the blue columns, though, because that's all there was in the lake. There was just no diversity in the algae. The lines are the nutrients. I'm going to point out a couple of things here. First of all, when you hear people talk about nutrients, especially locally, there's a lot of talk about nutrient ratios. And that's unfortunate. The nutrient ratios really mean nothing unless one of them actually becomes limiting. So we started off with nutrient ratios of 10 to 15 to 1, 10 nitrogen for 1 phosphorus, which is a ecologically balanced, if you will, nutrient regime. Well, let's look what happened by June. The nitrogen's gone. That's the green line. It completely tanked where this is limiting. There's just not enough there to support a lot of plant growth anymore. Meanwhile, the phosphorus, the black line, yeah, there was phosphorus used, but this isn't close to limiting for phosphorus. There's still lots of excess phosphorus in the lake at this point in June. And what was happening here it was the vegetation, the weed growth that was just gobbling up the nutrients as fast as it possibly could until it ran out of nitrogen. And that set the stage for the blue-green algae to explode through July into August. And then the algae crashed again. This, by the way, you wouldn't normally see such a crash. Always pay attention to your weather reports and your weather records when you're doing these sorts of studies. We had a big snowstorm that September, and the Fanazonan do not like snowstorms. And it not only knocked them back, but it looks like it just exploded their cells entirely because the nitrogen popped right back into the water, as you can see here. So that was the end of that algae bloom. But something I want to point out is between June and August, when your algae or cyanobacteria or blue-green algae were really exploding in population, the phosphorus increased. It didn't decrease. Now, important for me to point out, this chart is reactive nutrients. So it's not the total, but it's only the fraction of nutrients that is readily available for uptake by plants and algae. And even that fraction increased through the summer here, which is a concern. By the way, the stream flow into the lake kind of stopped around here. So this isn't simply flowing in from outside. So it points to strong internal loading. And this is the sort of thing that that's the re-release of phosphorus off the lake bottom. And that's the sort of thing that gets some people excited to start applying alum or applying different systems. Let's be careful and wait and do the math. Let's do step 1 properly, and then we'll see what's happening here. Okay, that's all I have to show on that slide. But this is really the interaction between nutrients and algae. And some of you may be saying, well, you just said it, Jay, you just said it was all about depth relationships. Okay, I'll show you how that fits in. Here's a more realistic prairie lake somewhat, because there's a big shallow area that has weed growth that the sunlight can penetrate to, right? So there's certainly, there's a better description of most of our prairie lakes. The sunlight penetration, as you saw in the previous graph, it supported a lot of vegetation that really stripped out a lot of the nutrient out of the lake. Just a little detail, an extensive weed bed on the north end of the lake, which is the end where the outflow of the lake is. Those weeds really stripped out nutrients because the water coming out of the lake was stripped of nutrients compared to the water that was sitting in the lake. And you just had to make it through that weed bed that was sucking up the nutrients. Okay. What did we learn about mixing in Kerr Lake? Well, weather events drive mixing right to the bottom. And so persistent stratification did not establish. What I mean by that is there was no thermocline that had cold water on the bottom of the lake and warm water on the top of the lake for any extended period of time. We saw temperature gradient in June, but not in any of the other sampling times. So when you put all this together, one thing that you learn from it is that these relationships do not support negatively buoyant algae, the stinkers. And these are some of the real healthy algae for lake ecology. And unfortunately, I think even in a reduced nutrient regime we're not going to see a great diversity in algae in Kerr Lake. You'll probably see some greens and cryptophytes for those that know algae taxonomy, but it'll be limited in terms of what can grow there. Interesting. Let's jump to the nutrient budget now that we have some feel for how the lake is working. As I said, the vegetation is very important to the nutrient budget. And, you know, I'm not sure if Brian Martineau is out there, but I know, and in Shoal Lake and in Kerr Lake, the weeds are your enemy, but at the same time, they're your ally against the blue-green algae. So some balance is what we're really after here. And that, as you saw previously, after June, the capacity of those weeds to soak up nutrients was just exhausted, and you saw the algae bloom, which raises an interesting little question. If that's the case, what happened? What would it have been like if we didn't have extra phosphorus after we grew up all the plants? Those plants would have held onto that phosphorus as best they could. You would have had some algae growth, but wouldn't that have looked different if we had just limited the amount of phosphorus in the lake to what the plants could soak up, right? Okay. Another thing we saw in our data is that internal phosphorus loading did coincide with a stable water column. So that June period especially, that pumped a bunch of phosphorus up into the lake. And how did we see this? Well, this chart, you probably can't read all the labels again, but I'll point out some of the things. This is phosphorus. In all of these four charts, the surface of the lake is on the left and the bottom of the lake is on the right. And we see some higher phosphorus at the bottom of the lake in June. That can point to different things, but let's look at something else. Here's your metals. Remember I talked about how metals can help you out? You can barely see them. This is the metals at the surface of the lake. That's what you should see in the lake. Here's the bottom. And specifically the iron and manganese signal, which are indicative of a changed oxygen regime in the sediments. It clearly shows that things have changed down there. Those are the same metals that bind up phosphorus. And so when the metals pop into the water, the phosphorus is popping into the water as well. Probably the reason we don't see as high a signal in the phosphorus is the algae were snapping it up as quick as it could come off the bottom. I'd like to point out one other thing here. I'll get the circle up, this yellow circle. This is your oxygen graph. And yes, oxygen was higher at the surface of the lake than at the bottom, but it was still above 4 milligrams per liter at the bottom of the lake. And that's, at 4 milligrams per liter, you should not be driving these things out of the sediments. So it just shows my point earlier that oxygen is a pretty crude way of measuring things. And so you really want to do some extra chemistry if you want to be confident in what you're seeing. So numbers, here's your first number for a nutrient budget. Based on all the chemistry, we came up with an estimate of 150 kilograms of phosphorus that came out of the bottom sediments during the year. Okay, well, let's look at how does that compare to what was coming into the lake with all that stream sampling we did. Here we go. Coming in the streams was 866 kilograms. And of that 866 kilograms, well, 96% of the phosphorus of the lake was external load from the streams. And so this pie chart shows it here. In terms of the phosphorus budget, I went back to Al Beck's estimates for the cottages and that sort of thing, because you can't really get it wrong. I mean, this is your residences. It's this gray line in here that you can't even see. So even if we underestimated, and I bumped his estimate up by a factor of 2 or 3, but even if we underestimated what's coming out of those cottages, this is insignificant. I guess one way of looking at it, I'll point out one other thing. This bigger blue piece here is the internal load, and the huge blue slice of pie is the stream flow load. So that much of the load is coming from the streams. And I think this internal load is a bit of an exaggeration of what things really look like, because I think if we hadn't dumped in 866 kilograms from the streams, we wouldn't, up until June, we dumped all that in between April and May, I guess, we wouldn't have seen 159 come off the bottom. So if you're me and you're looking for a place to focus on and maybe spend some effort and money on to remediate things, I'm going for the giant slice of blue pie right there. Okay, well, the giant slice of blue pie is the stream flow. So let's break it down a little further. There are 5 streams. Here's how they shook out. These are your 5 streams. And as it turns out, one of the 5 streams contributed 82% of the phosphorus. Well, how much is that? It was 713 kilograms of phosphorus. How much is that? Well, here's a comparison, and if you're not used to working in these numbers, that is 7 times the total maximum allowable discharge from the town of Neepawa on an annual basis to the White Mud River. So what does that look like? It looks like 7 towns of Neepawa all piled up around the shores of Kerr Lake, discharging their treated sewage straight into the lake. So is this a problem to address? I'll leave that up to you. Then just continuing with the numbers, the net load, so the load coming in versus the load coming out, was 382 kilograms. So in other words, we're still accumulating phosphorus in Kerr Lake, which means it's still getting worse after all these years, and will continue to get worse until we take some remedial actions. Okay. Wait. Did you notice the good news? Sorry. I'm going to back up a slide. There are 2 items of, this is the same slide I just showed you. There are 2 items of good news on here, and who can pick them up? I'll point them out. One is that most of the phosphorus in Kerr Lake that's currently contributing to the algae blooms that are happening is external load. Why is that good news? Because it's much cheaper and easier to deal with phosphorus on the landscape and prevent it from coming in than it is to try to get it out of the lake once it's in there. What's the other bit of good news? It's this. The total net load is 382. You've got 713 coming in one stream. So theoretically, if you do a nice job of cleaning up this one catchment, then theoretically, it's not perfect math at this point, you have to do some extra modeling, but theoretically, Kerr Lake becomes a net exporter, which means you clean up even one catchment, and then Kerr Lake starts to clean itself up. I think that's good news. Maybe I'm getting ahead of myself here. I'm getting into step 2 of success. And I'll go there in just a moment. But before I do, this is just more of the math. I won't dwell on this, but we can come back to it. But this is a picture I showed earlier. These are our sampling sites. And did anyone pick up on this green fringe around this little lake here? That's not good news. We'll come back to that in a moment. Okay, well, I think what we've done so far is a pretty good, thorough job of step 1 to success. We understand what's happening in the lake, and we know with real numbers how much phosphorus is coming into the lake, where it's coming from, and how much is cycling internally. That tells us where to focus our efforts if we want to start working towards success in remediating things. So let's take a head start on that. First, let's start on the good news that comes out of the study. Consider the phosphorus budget. I just pointed this out, really. So there's 159 kilograms internal, much larger external load. Most of that is from one stream, and yet your net accumulation isn't all that high. To me, this is good news. It would be nice to start working on these stream catchments, especially that one, to create some benefit to the lake. This question I just answered. Should we be focusing on internal loading or external loading? When people see a green lake, there will be people very eager to sell you systems to address the algae on the lake. Where would you like to spend your effort and money? In the lake or external? I mean, as we pointed out, in one stream, you might be able to turn the lake into a net exporter. And as I pointed out, I could build a career out of in-lake remediation, but there are many strategies around in-lake remediation: chemical nutrient inactivation, chemical algae inactivation, various chemical and non-chemical means of addressing weed problems, you name it. I mean, the little lakes across the US and in Europe, they've got operating budgets of millions of dollars a year. I prefer maybe somebody working with a front-end loader on the land to clean things up myself, because that's more practical and it's more preventative and a lot cheaper. But so we have good news here. There's still room for external land-based remediation. Harder news in terms of a head start on step 2 to success. I said that, you know, the low-hanging fruit, let's look at that one catchment that's providing almost all of the problem, right? That catchment has a lake on it, a small lake, a 30-acre lake, and it's that one with a green fringe. I mean, and so the chemistry, I looked at the chemistry in that stream, and it really shows that there's a long-term buildup in this catchment. And so what that means is a large accumulation in a small lake. So after just saying that it's better to do, or cheaper, to do land-based remediation rather than water-based, do we have to get into that lake after all? Well, first of all, it's better to do it in a 30-acre lake that's probably devoid of fish than in a big recreational water body. And one thing I'll point out is that we can look at this with science and know how much phosphorus, not only how much is in this little lake, but how much it's going to deliver to Kerr Lake and over what time frame. We can look at the sediments and other things to see what to expect. How long is this going to be a problem where it's exporting phosphorus to Kerr Lake? So that's where we are now. I mentioned earlier that the Assiniboine West Watershed District asked me for a work plan to do this work, to investigate this catchment and do step 2 of success, if you will. I just heard yesterday, unfortunately, that they will not fund further work on the project, at least not at this time. So that handsome little chap that we saw earlier in the presentation is asking, and maybe many people are asking, where do we go from here? You know, Kerr Lake is a beautiful, picturesque lake with a great recreational opportunity. At least it's beautiful from a distance. And when you look closely, it's not so much right now. But as I think this presentation and the study have shown, at this point we could go either way. Things could get a lot worse, or things could get a lot better. So where do we go from here? That's the question I'll end with and I'll leave you with. And Mike, I am ready to take questions myself. Actually, while you're sorting through some of the questions, Dennis, I remember one from last week. If you like, I'll just jump right in with that one. And I think I probably answered it in today's presentation, but I'll answer it directly. There's a question, do nutrients degrade once they're in the environment, or do they settle out in the catchments? And the way I'll answer that is to say yes on both accounts, and both will come back and bite you. What do I mean by that? Well, they'll degrade in that things break down and the nitrogen degrades and disappears. Through denitrification processes, the nitrification will end up in the air as nitrogen gas, which leaves the phosphorus behind. And that'll come back and bite you because what you're setting up is that phosphorus-rich environment, which those nitrogen-fixing, bloom-forming blue-greens love. And on the other hand, yes, nutrients settle out in the environment, and that'll come back and bite you, particularly the phosphorus. As I showed a little bit here, what often happens is the phosphorus just starts to accumulate in the lake bottom, and it might go unnoticed until the actual water quality of the lake degrades so that oxygen drops. And then all that phosphorus that's been silently sleeping and accumulating on the bottom gets released, and suddenly things explode into a much worse situation. So yes, the trick is to keep the nutrients out of the water as best we can in the first place.
Thanks, Jay. You bailed me out. I couldn't find my mute button. In terms of phosphorus budget, what can we do in the community ourselves to contribute to that? And like, how much of it can we do as opposed to requiring some scientific assistance with it?
Yeah, I guess with every situation, we have the specific lake in question and the specific environment in question, and you don't want to take a cookie cutter approach and say all studies are the same. So a little bit of careful thinking and planning is important. And then in every situation, we have different resources available. And by resources, I mean funding and money, as well as teams of eager volunteers that want to go out and do the sampling, or people that just want to wait for results. So there is a lot that the community can do. I pointed out the importance of understanding the various forms of phosphorus, but at the same time, just knowing how much phosphorus there is a big step towards understanding the lake. So I'd say in no case take an all or nothing approach. Let's all do what we can to understand our lake and be good stewards. And then sometimes, particularly where there are decisions to be made that cost money ultimately, in terms of should we apply technology, should we take control over some shoreline to prevent nutrients from going into a lake, should we buy an aeration system, those kind of expensive decisions, well, of course, they're best backed up by some science, right? So you want to dig in a little deeper than just the surface, I would say.
Can a community actually acquire their own testing and analysis device and work with someone in the science or biology end of it to interpret the results?
Yes, absolutely. I mean, this case study is an example of that. I provided the training to Colleen's staff. I wonder if Peyton is on this meeting. So Peyton was Colleen's fantastic technician through much of this, and I have to give commendation to her in name. With a bit of training, she did a great job of all those stream flow measurements and the sampling that she did. So sometimes that's what it takes, is a bit of training and a bit of pointing out. You know, things always come up in the field. I received many phone calls that were not officially part of this project, but I'm in the field and this happened. What do I do? Or, you know, this sort of thing. So it helps to, as you just mentioned, it helps to have somebody experienced in the field on call at least. But by all means, there's a lot of equipment out there. There's more and more probes. They get costly. They're in the thousands of dollars to really measure some of the more sophisticated chemistry. But then field kits for phosphorus and ammonia and these sorts of things, you're looking at, I think, $100 or so for some of it. And so it's certainly something that communities can do. I know in Shoal Lake, I met with the middle school and the high school and really encouraged them to get a monitoring program going, and that was a great program in their science program. The local schools can be, it can be a wonderful experience for all in terms of generating data on your lake and also inspiring the students to get involved in these things.
Here's an interesting one. What would it take to get Crown Lands regulations changed to a wildlife management area to prevent cattle and feedlot activities on Crown land?
Wow, I deal with regulations a lot, and I'm going to be careful not to sort of guess at that one. I mean, I think the question was get regulations changed or get a classification on a piece of land changed. And in terms of the wildlife management areas and that sort of thing, That's where I think we need to speak to the representatives, our local representatives in government, and speak to the right people and work towards a strategy that way.
And Jay, could you expand on your assessment that increasing the depth of Shoal Lake would have actually increased the algae weed growth there? And the comment is, seems to me that the lakes that are deepest have the best water quality. Weeds seem to do better in the shallow waters.
Yeah, and depending on which lakes we're referring to, I mean, we all know that a lake like Lake Tahoe or our deep Canadian Shield lakes tend to have cleaner water than a shallow prairie lake. But that it does not follow that adding a foot or two to a prairie lake makes it cleaner. And in the Shoal Lake situation, do some free consulting here, but a lot of the weed growth was just on the cusp of getting any sunlight. And it was generating oxygen. Actually, we saw higher oxygen at the bottom of the lake than at the surface in some conditions. And if you raised the water level, a couple of things would happen. You cut off the sunlight from a large portion of the lake. So these are your deep weeds would no longer grow. And the bottom would go anoxic and really fuel up more internal loading of phosphorus. Now there was a lot of phosphorus there. The other thing it was doing, great comparison, Shoal Lake looked to most people the same as Kerr Lake in that it was green, stinky, had scums of blue-green algae on the surface which collected along the shorelines, on the weed beds. But when you actually looked closely, it was completely different in the algae ecology. Even at the height of the worst blooms we saw in Shoal Lake, the diatoms, which are your fastest sinking algae, they were keeping up with the blue-green step and step. And it was a very diverse algae ecology, but they were just barely doing it. And if you added 2 feet, what would happen is those diatoms would settle out, the blue-green algae would get a competitive advantage, take all the nutrients that the diatoms have been fighting them for, and it would also allow the blue-green to set up at the surface, and the whole lake would would more likely look like those shorelines that we've come to, that are just quite putrid, honestly. Yes, you can make things worse than we've seen in Shoal Lake. I think what's happened in the past, I received many conflicting reports in terms of when the algae was worst, because people's reports and photos tend to support the argument they're trying to make, and piecing them all together. What we saw is...
Hello. It's a couple of days after the original workshop of January 20 now, and we thought it would be helpful to add this little clip now that I've had a chance to hear the question a little bit better. The questioner suggests that the deeper lakes are healthier than the shallower lakes. It would be really nice to have dialogue with the questioner to be able to refer to the specific examples that they're thinking of. But for now, we have 2 examples that we've been talking about. That's Kerr Lake and Shoal Lake. So let's look at those. Between the 2 of them, Kerr Lake is deeper. Shoal Lake has higher phosphorus concentrations, believe it or not. And the more intense and the more prolonged algae blooms are on Kerr Lake. So how does that work? Well, since we've studied the 2 lakes, we know how that works. The differences in those depth relationships in the 2 lakes cause them to take different paths from spring into those summer algae blooms, even though the summer algae blooms might look similar in the end. And if you were to increase the depth of Shoal Lake so that it functioned more like Kerr Lake, well, the results might not be pretty as long as there's that much phosphorus in the lake. So I won't take the time for a full explanation now, but I touch on pieces of this in my original response to the question from the other evening, which we will go back to now. Thank you.
When Shoal Lake was high, we were having a lot of high flow events, and there was a lot of flow through the lake, which was contributing to the mixing and the flushing of the lake. And so it does not follow that to hold the lake that high when there is no flow through the lake on a dry year, it does not follow that you will have sort of some of the better conditions that we're seeing in some of those years. So there's a lot of complexity around the question and the answer, but I think that speaks to some of that complexity.
This is a longer one. You talked about preventative measures, including altering the land to prevent phosphorus loading, rather than trying to remove the phosphorus from the lake after the fact. You also talked about using a front-end loader, for example. Ditch Lake has about a 4x10 ditch running into it from the north and along a roadway entering the cottage area. It runs downhill from elevated ground north of the lake. How would one go about perhaps altering that carrier of water and the phosphorus that may be in it into the lake? Not specifically, but in general, what are some of the examples of diverting that water?
Right. So we're talking about a different lake than Kerr Lake here, right?
Yes, this is Ditch Lake.
And okay. And that's where, I mean, you need to work within the topography you have, right? I'm not sure how much space we have there, but, and where is the phosphorus originating from? I mean, I'm the lake scientist, but usually the solution to your problem is look farther upstream. And as it turns out, if you look far enough upstream, sometimes you have to climb right out of the ditch or the stream onto the land itself, right? So I'm not familiar, unfortunately, with that spot on Ditch Lake, but I think that's what it would come down to is go out in the pickup truck and have a look around, have a look at the topography and see what options are available there. I'll say that simply turning something into a wetland is an oversold approach, because wetlands don't have infinite capacity any more than other bodies of water do. So they, if people are monitoring phosphorus coming out the back end of a wetland, it looks great for a few years and then you get flow through. So it needs to be a little bit more, plan farther into the future than simply that.
It apparently Ditch Lake, that stream running in, they feel contributes about 60% of the phosphorus, and it is coming from surrounding agricultural land.
Okay, that, I mean, to me, that sounds like a great opportunity. It's nice to have one spot to focus on rather than, you know, point sources spread all over the place, or non-point sources as they call them. So I'll tell you what, if anybody would like to follow up with me on that Ditch Lake, I'm just not sure what to say because I can't picture the landscape and the topography there. So it's hard for me to say. There's no magic bullet in any of this stuff.
Sure.
There are expensive solutions, but there's no magic bullet. I mean, that's why I say you kind of need to work with the local guy with the front end loader or the landowner himself and configure things out better sometimes than trying to buy a system that fixes the problem.
These were comments and questions posed by Randy Abbott, and he'll share that study with you, which there actually was a study done there in 2011 by University of Brandon. A water quality study was completed there. So he'll share that with you later.
Okay.
Are there any alternate techniques for aerating or oxygenating or mixing lake waters, and under which circumstances might those be most effective?
Yeah, there are many techniques. I mean, you touch on two families of them. So aeration systems, part of the reason I really dwelt on the relationships among depths is that gives us a launching point to start talking about aeration systems. What are we trying to accomplish with the aeration system? So, I mean, sometimes it's providing open water in the winter so that there's oxygen for the fish to survive. But I think what we're talking about are summer aeration systems or oxygenation to try to improve algae blooms. And in that case, what are we trying to accomplish in the first place? Are we trying to deliver oxygen down to the sediments to prevent anoxia and prevent internal loading? Are we trying to speed up vertical mixing enough to prevent the floating, the cyanobacteria from outcompeting the sinkers? Are we trying to just put them in a jumble to take away the competitive advantage that they have? Are we trying to increase circulation? Are we wanting not to increase circulation? Many of the systems have to be geared so that they do not upset the vertical stability of the lake. And I've seen that done more with oxygen systems rather than aeration because it's a more potent dose of oxygen. I've seen nitrate pumped into lake bottoms as an oxygen source because they did not want to create any bubbles. So I'm not sure if I'm answering exactly what the questioner wants me to answer, but I think I'm pointing to, before we ask what will work, let's ask what we're trying to accomplish very precisely. And once we know that, we can go to a system that will accomplish that for us. But yes, there are many types, I mean, even in aeration, there are the coarse bubblers, there are the micro bubblers, and there are the nano bubblers, and different configurations of each. So there are different systems, definitely.
And that's another scientist comments as well, supporting that too, that science, in fact, is so important to understand the issue in protecting our water bodies. And just a comment at this point. If a community were to conduct a luminological assessment, how could they go about that? What would they have to do?
I'll try not to be too triggered. Hire a limnologist. I mean, really, it comes down to, there are many things to focus on, and I'll always say, don't take a cookie cutter approach. One study should not look just like the next study, should not look just like the next study, because every environment that we step into is different, right? And so that's where I think it takes some experience to recognize, oh, on this lake, we should focus on the hydrology flowing through it. On this lake, we should look at, or this reservoir, we should look at the hydraulics of the vertical mixing. On this lake, we should look at what's happening with the chemistry of the bottom. And I mean, ultimately, you want to have some understanding of all of these things. But I think no one has the budget to really give thorough study to every one of these last things. So it takes some experience to recognize what to focus on. Right? And limnology includes the fish too. You know, the fish community and the aquatic ecological community. So, and that both tells you a lot about the lake and points to some things that need to be done for our lake.
Does low levels of dissolved oxygen in lake water impact phosphorus recycling?
It can. And as I pointed out, what we saw with that 159 kilograms of phosphorus coming off the bottom of Kerr Lake, it really looked like that was redox mediated internal loading, meaning changes or a drop in oxygen level in the sediments, which created a change in the chemistry of the sediments, which released these compounds, including the phosphorus. So it certainly can. It's one that people focus on, sometimes forgetting that there are other ways that phosphorus can come out of the bottom. And there are many biological mechanisms that are created by the worms and the invertebrates living on the bottom, or by the plants growing. Carp can be part of it, boats can be part of it, different mixing that way. So there are quite a number of ways that phosphorus can come out off the bottom, but a common one that's focused on is precisely that, the change in oxygen levels.
This is a kind of combination comment and question. So is it safe to say then that you don't want to just harvest or remove all of the surface weeds and or pull or bulrushes in the hopes that you'll improve water quality and prevent algal blooms? You're saying it takes a much more calculated approach?
I would recommend a calculated approach. I don't mind the notion of removing weeds for a couple of reasons. One is well, let's look at it this way. I've seen people spending money on floating cattail mats and that sort of thing, right? Well, cattail mats have trouble in the wind and there are other problems associated with it. But why would you go to that trouble when you've already got weeds that are sucking up nutrients? So that's one way to look at it. Another is it serves different purposes. At the boat launch, people want the weeds taken away, right? And so there are different purposes. And I know they're looking at, I believe they're looking at that at, in Minnedosa Lake. There is a place for that. Another nice thing about it is it's action and activity that's very tangible. And that can go a long way in communities that would otherwise kind of feel hopeless if they don't see anything being done on their lake, right? So, so it's nice to have real action on a lake, especially when it can be done largely with volunteer. Now, yes, I take a calculated approach. Why not do the math and know how much phosphorus you can reasonably remove from a lake? I mean, it's simple math to do. Those weeds are probably around 2 to 4% phosphorus. So how much trucking do you need to do to take it away? And the other thing about taking away weeds, do it with sensitivity to the environment. Yes, the weeds have a place, and they're a very important part of fish habitat. They're a very important part of migratory bird or waterfowl habitat. And you don't want to just start tearing up the sediments, because you will create more of a problem than you're trying to fix if you're pulling up sediments and releasing phosphorus that way. And I heard you mention weeds and bulrushes. Let's be very careful about the ecology of things here. The weeds we're looking at in Kerr Lake are just an overabundance of Myriophyllum and Ceratophyllum, which are those bottom weeds that are very loosely, actually the Ceratophyllum don't even attach to the bottom at all. They just tangle themselves up in everything else. You can carefully remove some of those without impact to the aquatic habitat. Bulrushes, I would be hard pressed to think of a place where it would be good to remove bulrushes, because they are important habitat and they're real shoreline stabilizers. You can just picture the wind coming on the shoreline. So be careful about, which weeds you're removing. Don't just go attacking everything, because you'll do more harm than good.
This is a combination comment and question, but the primary, and it goes back to the aeration discussion, but the primary purpose of lake aeration is really to create new recreational fisheries in lakes that are devoid of fish, like Patterson Lake or like Rossman Lake. Given the importance of angling in this area, could you please comment on that?
Yeah, sure. And that actually fits in with my answer, I think, when I said with aeration, you want to be precise about what you're trying to accomplish. And in those lakes, I believe still they're running the aeration just in the winter. What you're trying to accomplish is maintaining oxygen through the winter, because those lakes, once they get ice covered, the oxygen drops through the winter, and they would not have sufficient oxygen to sustain those trout that are that great resource in terms of local anglers and tourism as well. So you're specifically trying to create open water in the winter, and once you know what you're specifically trying to do, honestly, any number of aeration systems would do that well. So yes, that's a great application, and it serves its purpose well.
Can a community install, you were talking about flow rate, and can a community install their own flow meter metering device and monitor that on their own?
Oh, absolutely. It's really a technique and a tool. The simplest tools are, now they've got Doppler systems and all kinds of things that I didn't have the privilege of using through most of my career. But the simplest tool is simply a little propeller on the end of a counter, and you hold the rod in there, and you're measuring velocity, and then you also measure depths and widths, and you do the math, and you come up with a stream discharge measurement. So especially for small streams, I could certainly provide the method and the techniques, and it's not an expensive output. That's in the hundreds of dollars into $1,000 or so for a good flow meter.
What other methods could we use in our community to remediate lake health apart from aeration or apart from wetland structures? I guess what have been effective in terms of what you have seen around the variety of lakes you've experienced?
Yeah, it comes down so much to the individual issue that your lake is facing. And I really feel like echoing something that Bruno said last week is that our number one problem in all of these lakes is nutrient loading. And so I don't know if we're ready to start applying in-lake management techniques on a lot of these lakes. The sticker prices will be a shocker when we get into those sorts of techniques. So I'll really urge look for ways of keeping nutrients out of the waterways. You know, the standards are buffer zones and this sort of thing, but put some thought into it. I mean, nature doesn't work in lines, and so consistent with the buffer zone along the stream doesn't necessarily make sense. What you want to look for are those low spots that are accumulating water and accumulating nutrients and delivering them to the stream. So really start there, and then after that it becomes hard to talk in generalities in terms of what works and what doesn't, because as I said, you have to start off with knowing the problem first. And I mean, there's a big problem, the nutrient loading. So.
Are lakefront residences a significant source of nutrients into our parkland lakes? I know you commented a bit about that in your study.
And my answer will be, they can be. Are yours? And what I mean by that is I wouldn't put out a blanket statement for all of the lakes out there. I don't think they are in Kerr Lake, although that's contributing too. And you can only advise good management practices for your septic systems and that sort of thing. You wouldn't ever want to cut corners there. But what we saw in Kerr Lake, I mean, whatever's coming off of those cottages is really dwarfed by that one big stream. In another lake, it might be a very different scene.
It's been very interesting, Jay. Appreciate your response to the questions and really appreciate all of the participants' questions. You did an excellent job tonight, and thank you for that.
Well, thank you. I do appreciate it.
Thank you very much, Jay. Very enlightening presentation, as well as the answers that you gave to the multiple questions there. And thank you, Dennis, for your assistance. In closing, I should say our next workshop is on January the 27th at 7 p.m. again. And we have Brian Martineau and Barry McPhail of the Friends of Lake Minnedosa giving us a presentation entitled Save the Lake Project. Good evening, everyone, and thank you all for joining us. All the best to you and your families. Until next time.